Hi everyone. So today we're looking at a Year 12 level geometry and trigonometry question where we need to find the volume of a trash can. So here's the trash can we're looking at, and you can see it's made up of two parts, a cylinder part at the bottom and a hemisphere at the top, so half a sphere at the top. So the first part of our question says write down the height of the cylinder. So as we're looking at this, we can see that from the bottom up to the top is 70 centimetres it would be. It's not going to be 70 metres, is it? It wouldn't be 70 millimetres either. So 70 centimetres. And we're also told that the radius of this base of the trash can is 20 centimetres. So if we think about that for a minute, 20 centimetres is the radius of the base, which must mean that 20 centimetres is also the radius of the top. Now, if you think about a sphere, here we've got a sphere, and so 20 centimetres, because we've sort of chopped that off, haven't we, for the top here, 20 centimetres would come in to our middle point of the sphere, so into there, that would be 20 centimetres. And then if that is the true radius, that should also be 20 centimetres up to the top, shouldn't it? So this line going up here should also be 20 centimetres. So write down the height of the cylinder. Well, the height of the cylinder is going to equal, let's do height as a capital H, height equals 70, take away that 20 centimetre height for the hemisphere, because we're just trying to find the height of the cylinder, just this length here. So 70 take 20 equals 50 centimetres. Okay, part B, find the total volume of the trash can. So looking at our trash can, again, we already discussed in part A how this trash can is made up of a cylinder and a hemisphere. So when we're going to work out the volume, we need to think about the formulas of those shapes. So here we've got the formula for a sphere, which would be a full, or two lots of hemispheres, wouldn't it? And then we've got a cylinder. So when we come to use this formula, we just need to remember to halve it, because we're only dealing with half a sphere. So when we write this down though, so the volume of this trash can will equal the volume of a hemisphere plus the volume of a cylinder. And then we just substitute in these formulas up here. So hemisphere, we're just going to write it like this for now. So we're going to halve our sphere formula. So 4/3 pi r squared, cubed, sorry, plus our cylinder formula, pi r squared h. And then, now that we've substituted our formulas in, now we just need to substitute into our formulas the radius from our trash can, which is 20 centimetres, and the height, which we worked out in part A, was 50 centimetres. So we're going to rewrite this as half, 4/3 pi, and in here I'm just going to substitute in the 20 centimetres cubed plus pi 20 squared times 50. Substitute all of that in, and then my pre-prepared answer, you get 79587. And because we're working centimetres, this is centimetres cubed. And then if we're rounding to three significant figures means we would put a bit of a cut line in there. And so because that is an 8, we're going to round up that 5 there to a 6. So we get 796, and these two digits just become zeros. So that would be to three significant figures. All right, part C. a designer is asked to produce a new trash can. The new trash can has the same shape as the other one, but the new trash can will have a height of h and a radius of the base of r. So we're not told what they are yet. But there's a design constraint so that the height plus 2 lots of the radius must equal 110 centimetres. And the designer also has to maximise the volume of the trash can. So try and make it as big as you can with those constraints. Find the height of the cylinder. So not the whole trash can, just the cylinder. So just find this height here. And I should just block these out now because in this part of the question, we're starting without any figures. We're just sort of coming up with a formula for it. So find the height of the cylinder h of the new trash can. So we're trying to find out that height there, just the cylinder height. So if we think about this for a minute, we're told that the overall height plus 2 lots of radius equals 110. That's something we're told. But think back to in part A, where we had to work out the height of the cylinder. What did we do in part A? Well, we said this is the full height, and that was 70, and we worked out that the radius there is the same as the height of the hemisphere, because the hemisphere, the radius is the same all the way around. So if we go 70, take 20, then that sort of cut off that hemisphere on the top and just left us with 50 for our cylinder. So we're going to do the same thing again, except we haven't got any numbers to work with. We're going to be left with just formulas. So our height in this case, our cylinder height, little h, will equal the big height minus the radius, because the radius across or up is the same, it's the same length. So the height of our cylinder equals the overall height minus the radius. Now, to make this into a bit more of a useful formula, given the other information here, we just need to work out what this h is. So if we can use this information here to work out what h is, then we should have a formula for our cylinder height, which gets rid of one of these variables, because at the moment we've got 3 unknowns here, 1, 2, 3, and 3 is a crowd. So usually you want either only 1 or 2 unknowns. So if we just work over here, so we're told that the height plus 2 lots of the radius equals 110 centimetres. And so we can just rearrange this formula. If we subtract 2r from both sides, then those 2r's cancel out, and we're just left with h equals 110 minus 2r. So we're going to take this information and we're going to substitute it into this formula here for our big H, because big H is just the same as that. 110 minus 2r is the same as big H. They're the same value. So what we can do is, over here we'll substitute in 110 minus 2r, and then we've still got another minus r on the end. So if we clean all this up and get rid of the brackets, we're left with 110 minus 3r. And that is the height, or the formula for the height for the cylinder part of our trash can. All right, part D. Show that the volume of the new trash can is given by, and I haven't got the rest of the question there because there was actually a mistake in this question. So what we're going to do is we're just going to change this question to say, calculate. And so we're going to calculate the volume of the new trash can using the information from part C. So calculate the volume of the trash can. So this is a bit like in part B. So we know that the volume of the trash can is made up of volume of a hemisphere plus volume of a cylinder. And so now we're just going to substitute our formulas back in for those. Here are our formulas up here. So hemisphere again, half outside of 4/3 pi r cubed plus volume of a cylinder, pi r squared h. Now this time, the difference is that we don't know the radius, and we have a formula for h which we worked out in our last question. And here's that formula just to remind you. The height of the cylinder equals 110 minus 3r. So we're going to go through now and substitute that in. And as we're doing that, I might just clean up some of this stuff as well. So think about 4/3, like what's half of 4/3? Half of 4/3 would be 2/3. Just like half of 4 is 2, half of 4/3 is 2/3. So we can simplify this, and you can do it in your calculator if you're not confident to do that in your head. So we've got 2/3 pi r cubed plus, over here we've got pi r squared, and then we're going to substitute this in 110 minus 3r. So this first part's going to stay the same, pi r cubed. When we get over here, we just need to expand this bracket. So we go the pi r squared here times 110. So we're going to get plus 110 pi r squared. And then the pi r squared times negative 3r. So we get minus 3 pi r cubed. Now, we can go one step further. I'll just write in here just how we did that. So we did that, and then we did that to expand it. And you'll see here now in this last line that we've got two terms. This is just like back in grade 7 algebra, although it just looks a bit messier now. But we've got two terms here which are both r cubed terms. And so that means they're like terms. So we can sort of put them together, and we should finish up with just a pi r squared term and a pi r cubed term. It's just like you can't add an x and an x squared term. So if you had 2x plus x squared, you would have to leave it like that. You can't write that as 3x squared or 3x or something. You can't, they're different things, so you can't just combine them. Same here. So we've got an r cubed, an r squared, and an r cubed. So r cubes we can group together because they're like terms, but the r squared has to stay by itself. So the trouble is here, if you're doing it in your head, we've got a fraction and we've got a whole number. So these are our coefficients, remember, out the front of our terms, coefficients. And so to be able to add and subtract those, we need them to both have the same denominator. So the way that we would change, I'll use a different colour. So over here we've got 2/3, which is a fraction of thirds. Over here we've got the number 3. So if you think about the number 3, how many thirds are in 3? Well, 3 represents 3 whole things, doesn't it? So how many thirds are there in those 3 drawings? There's 9 thirds altogether. So this number 3 is really like 9 thirds. And so what we're going to be doing is we're going 2/3, take away 9 thirds. So 2/3 minus 9 thirds. So think about your number line, you're up at positive 2/3, take away 9 thirds is going to drop you down below 0. We're going to end up down at negative 7/3, negative 7 thirds. And of course you can do that in your calculator if you find that confusing to do in your head. So combining these two terms, I'm just going to write this one first because that's a nice positive one to lead with. So pi r squared, and then we've got negative 7/3 pi r cubed. And that is the formula for our new trash can with those restrictions on it. Okay, part E, using a graphics calculator, find the value of R which maximises the volume. Now, in our last part of the problem, we came up with a formula for our volume, and that formula, if we graph it, should have on it a peak, so a maximum somewhere on the graph. And if you have a look at the screen now, you can see the graph that I've done on Desmos, and you can see there that peak, which I've highlighted. So I've just put that equation that we came up with in part D into Desmos, and you would just do this on your graphics calculator, and then you'll get a graph like that. You find the peak, and that peak is telling you the value of R, so the radius, which gives us the maximum volume. And that's what that graph is showing us. And so it's just a matter of graphing that, and then you just need to find the peak, and you can do that using the analytical buttons on your calculator. All right, part F, last part of the question, and I'm sorry the text has come out really small for this, so I'll read it for you. The designer claims that the new trash can has a capacity that is at least 40% greater than the capacity of the original trash can. State whether the designer's claim is correct. All right, so first of all, we need to find out the new volume of our trash can, its maximum volume, and then we need to compare that to the original volume and see if it's at least 40% greater in capacity, and that will prove their claim. So let me just write down the original volume for you, just so we've got that in our head. So we calculated this back in part B, and we said the original volume was 79587 centimetres cubed. That was our original volume. And so to work out the new volume, we're going to do the same process, but we're going to use that formula that we came up with, and we're going to use that maximum radius value that we came up with. So our new volume will look something like this. So it would be 110 pi squared minus 7/3 pi r cubed. That was the formula that we came up with for our new trash can, given the restrictions on it. And we're going to substitute in now the radius, which gives us the maximum volume of our new trash can, which from part D, we found on our graph, the maximum point, the radius was 31.4. And it was a longer decimal number than that, so make sure you're actually using the longer decimal number, otherwise it will affect your accuracy. I'm just writing the short one, 31.4. And so chuck all that into your calculator, and you should get 113,781 centimetres cubed. And so now there's one last step. We just need to compare this new volume to the original volume and find out if this is 40% greater. Is it at least 40% greater in capacity? And so the way that we do that, we use our percentage error formula essentially. So change in capacity, because we're trying to see a similar thing to like you would with the percentage error. You're trying to see how far off the actual or the estimated values were. So you're trying to see how far apart the actual and estimated values were. Here we're trying to see how far apart the original and the new values are. So it's the same process. And so what we do is we're going to go 113,781 minus 79587 over 79587 times 100%. And if we do that, we get 43% as our answer. So the designer claimed the new trash can has a capacity at least 40% greater. Is that true? Yes, it is. The new trash can is 43% greater. So they made the right claim.